Just thought I'd do a quick tutorial or demonstration on how I'm making a thermostatically controlled heater controller box using one of these cheaply and readily available STC 1000 thermostatic controllers. This is the 12 volt version because I had it already from a previous 12 volt heating application using car batteries and a solar panel, but it didn't really work out, so I'm going to repurpose this into a 240 volt controller to power a 240 volt heater. So obviously you're going to need the thermostatic controller and the temperature probe. I'm using this project box, readily available. The input power is going through a IEC connector with a built-in fuse. There's the fuses for that. I'm going to use a 3.5mm audio jack for the temperature probe. Now, because this is a 12 volt powered controller, I need a 12 volt transformer to step the mains 240 volts down to something that this can use, which is why I've got this transformer. This transformer is way too big, but I already had it, so I'm going to use it. This circuit breaker goes on the input side of that transformer because the 10 amp fuse is obviously way too big. This 3 amp is probably still too big. I might change it to a maybe like a 500 milliamp fuse later down the track. I've got an on-off switch which will switch the mains input on the other side of this input socket. Now for the step down transformer, because it's 12 volts, this is on 12 volts, I decided to get a 12 volt relay. This relay will switch the heater. It's a 10 amp relay, double pole, double throw, because the relay that's built into here, although it says 10 amps, I do not trust it because I've seen in here what's actually in here, and the relay is like the size of my thumbnail. I wouldn't trust that with 2400 watts, so I'm going to use that to switch this much bigger relay. On the other side of that relay, the power will just go straight to this output socket, so I can plug literally any kind of heater into it. Because this is a 12 volt DC coil, I've got a 12 volt, I've got a full bridge rectifier and a electrolytic smoothing capacitor that'll smooth the AC coming out of that transformer into DC that the relay and the STC can use. And I've also got, of course, some salvaged mains wiring from an old extension cord I'm going to use to wire up this box internally. Assortment of connectors, strippers and crimpers, anti-multimeter for fault finding if it doesn't work. I mean, if you know what you're doing, you shouldn't really need this, but you know, if you're doing any electrical work, you should have one of these anyway. This is the circuit diagram that I'm going to follow. It's what I've come up with. What we've got is 240 volts coming in from the mains, going through the 10 amp fuse that's built into the IEC, through the on-off switch, and then it's split into the smaller circuit breaker for the transformer, and then split down to the big relay for the output. On the other side of this transformer, that's going straight to a full bridge rectifier with a smoothing capacitor. Then the 12 volts DC from here is powering the STC controller, and it also goes across to the heating relay. Obviously the thermostat is on its own little thing with the 3.5mm socket. The negative or common of the 12 volts goes to one side of the relay coil, this big relay, and then the switched side from the thermostat controller goes to the other side of the coil. So often the most time consuming and difficult part of making a project like this in a ABS housing is mounting all the hardware inside the box. Now, because I've used such a large transformer, it's taking up the most space and it's the heaviest thing, so I wanted to put it in the middle of the box just so that when you pick it up it doesn't fall out of your hand in a particular way because of the weight. You want the weight to be central. But because it's so big, I'm going to have to squeeze all the other components around the outside of it in a way that they don't interfere with each other and the wires don't cross over too much and risk having short circuits and that sort of thing. So it just takes some careful thought and practice really to know where to put things. There's no hard and fast rule about how to do it. You just gotta, you measure your components, usually squares and circles and things, and then you sort of lay them out roughly where you want them, and then you scribe lines or draw lines with a texter. Try and get the things central and make it look decent and square. With the things on the inside, I just sort of put them in place and drill holes through. Maybe I'll drill one to pin it, put a screw in, line it up roughly square, and then drill the other one and put the other screw in to hold it down. And things that need large square cutouts, I mean, stuff like this, you just drill some holes and bolt them down. But things like this connector and the output socket and the temperature controller, they need a large rectangular hole. So the process I used, I'll demonstrate on the biggest one. Well, I've already done it, but I'll explain what I did. Well, say I wanted to get it perfectly in the middle and somewhere reasonable up from the bottom here. So you measure the outside dimensions of the box. You measure the outside dimensions of what you want to put in. So, the hole size that you need. And I've been using verniers for this because they're more accurate than a ruler. Ruler's fine if that's all you got. You can measure the dimension of this, divide it by half. That'll put you right in the middle. And then you subtract half of the dimension of that to get you this one. And then you add to that number, or you scribe a line at that mark. Then to that number you add the entire dimension of that, and that'll get you to over here. Scribe a line. Same thing from the bottom. Decide how far up from the bottom you want it. Scribe a line. Then you add the dimension of this to that number to get you that top line. Then all I've been doing, drilling holes on the inside of the lines and knocking them out with a screwdriver or whatever. I've tried in the past using things like cutoff wheels on plastic, but it just melts the plastic, makes smoke and a horrible smell. It's actually easier to drill them. Quickest way to remove material is with the drill bit. Just drill inside the lines and punch it out with a screwdriver. And once you've knocked out all the interconnecting pieces with the screwdriver, you just twist the bulk of it out like that, and you're left with this horrible rough hole. But all I do at this point, because I find it easier and I get more control, I just grab myself a file and start filing away until I get down to the lines that I've scribed. This ABS plastic files really well, just makes a huge mess with the dust and the microplastics, bad for the environment, whatever. But I find this is the easiest way for me, and I get a more accurate hole with a file. And once you've attacked it with a nice sharp coarse file, you end up with something like this. And the good thing about a file is you can use either the square one or a triangular one to get nice sharp corners, and you get really clean straight edges, and whatever you're trying to fit in the hole just goes in nice and snug like that. You can see it's very square to the bottom edge. Looks very professional, or more professional. Looks as professional as you can with a hobbyist grade enclosure like this. And with the circular ones, obviously it's easier. It's nice and easy to draw. Just use a hole saw, or you can use the drilled holes and knock it out method if you don't have hole saws. Important thing is, if you're putting a round thing in with a square bolt pattern like this, what you want to do is drill the big hole first, get it in there, and then just use this as a template to drill the 4 holes to bolt it down. I find if you drill those 4 holes first and then try and do the big one, you've almost got no chance of getting the big hole lined up with the 4 square ones. This socket didn't really come with a template apart from the rubber gasket, but I find it's easier just to drill the big one, get it in there, line it up nice and square, and use that as a template to drill the 4 holes to bolt it down. Well, we're pretty much finished all the mechanical mounting of all the hardware in the 2 halves of the enclosure. Like I said, this part of the project takes the longest, so I think because it's getting dark out here now, we'll move inside to do all the wiring. So here we are with the finished product, all wired up. I didn't film any of the wiring job because it was too fiddly and cramped in here. I couldn't really get a good shot. But basically what we've got is the power coming in through the IEC connector, going straight to the on-off switch. I have also connected through the earth pin of the IEC connector on this green and yellow to the case of the contactor, and then through to the output socket. Very important for safety that you connect through the earth wire to the output socket. On the other side of the power switch, I have twisted 2 wires together to give extra current carrying capacity. That's the main load wires going to the normally open side of the relay contacts. I've also got one active wire going to the circuit breaker and 1 neutral wire going to the transformer. Other side of the circuit breaker active goes to the transformer. The output of the transformer, I'm using the 12 volt AC output. I did try the 9 volt with the smoothing capacitor, but under load it was down to like 11 volts. So I put it on the 12 volt AC output. With the smoothing capacitor, it's the relay and the controller are getting sort of like 14 volts under load, which I think is fine. The output of the transformer goes straight down to that full bridge rectifier. The negative of the full bridge rectifier is split to the STC controller on this purple and yellow wire, and then the other purple and yellow wire goes to one side of the relay coil. The positive output of the rectifier goes to the STC controller and is also bridged across to the heater switched output, and the other side of the heater switched output on this red wire goes to the other side of the relay coil. And of course the common terminals of the relay, the main load carrying wires, go out to the output socket. And I've also got the temperature sensor wired in there. You can't really see it down there, with a 3.5mm audio jack. So time to throw some zip ties at it to loom the wires together a bit nicer, and we'll close it up and give it a test. And here is the finished product, all wired up and reassembled with the temperature probe plugged in on the 3.5mm jack. So when I turn it on, I have it connected to a light here above the bench, just for demonstration. So with the temperature probe, I can just warm it up with my hands. You'll see that when it gets to 20, the light should turn off. There we go. So at 20 degrees the light turns off. And if we get it back down to 19, you'll see that it turns back on again. There you go. Works pretty good, I have to say. So the use case for this that I designed it for and made it for is to control the heater in a greenhouse. Overnight temperatures here can get down to 0 degrees in the middle of winter, and got some plants that aren't supposed to go below 16 degrees Celsius. So I'll connect this to a little fan heater inside the greenhouse, and yeah, should keep the plants happy overnight on those cold winter nights.